All right, so here comes the super secret stuff. Okay, so now what we're doing is we're going to talk about this protein SL1. And SL1 is regulated by acetylation. And acetylation, when the protein is acetylated, it binds better to DNA and it can increase transcription of the ribosomal RNA. Its acetylation is removed by this enzyme sirtuin-1. And so the idea that we had with this was that if we blocked sirtuin-1 or got rid of sirtuin-1, you should get more acetylated TAF68 and you should get more ribosome biogenesis. And if ribosome biogenesis is important in muscle hypertrophy, we should get bigger muscles, more muscle hypertrophy. And sure enough, when we did the first experiment, we took the SIRT1 knockout mice. These lack SIRT1 in their muscle, and we did overload with them. Here are the wild type animals. We see a nice increase in muscle fiber size. But when we look at the SIRT1 knockout mice, we're actually seeing almost a twofold better increase in muscle fiber size given with this exact same amount of overload. So when we decrease SIRT1, we get a doubling of the amount of muscle hypertrophy from the same amount of exercise. So that's super cool. It goes with our hypothesis. And then the next thing to do is to say, okay, but this is a transgenic animal. It's a knockout animal. So what happens if we use a drug that's specifically designed to block SIRT1? Can we see the same thing? Sure enough, when we injected splitamycin, which is a drug that blocks sirtuin-1, and we did that every night, what we saw is that we saw about a 77% greater muscle hypertrophy in the animals that were injected with splitamycin than the ones that got saline instead. So this is super cool. You don't even need to have a genetic knockout of sirtuin-1 to benefit by getting bigger muscles. What we can do is simply acutely block SIRT1 while we're doing our resistance exercise, and I can get bigger swole than you from doing the same exercise. So this is cool, but again, you're injecting something that's a drug. It's going to be quickly made into something that's illegal by WADA. So now the question becomes, can you figure out a way that you can do this where you can go in and use different nutrients to target sirtuin-1, to block it, and then can you use that to increase muscle growth? And so what we did is we went through this process of we identified 3 different nutrients. They're natural products that are naturally available in regular foods. And we did this really cool little set of experiments where we do the equivalent of a couple hundred different experiments in one experiment. And what it does is it produces a model that says this is which of the nutrients are working, and this is how much you need to use of them. And so what it does is it generates this model that says if you add this much of nutrient 1 and this much of nutrient 2 and that much of nutrient 3, you would get this much extra hypertrophy. And if you added less of them or different amounts, you would get this. And so what you can do is you can say, what's the optimal combination and concentration of those nutrients to maximize the increase in muscle fiber cross-sectional area? What's the least beneficial? So it's the same 3 nutrients, but we now put them into a combination that isn't as optimized for muscle growth. And then we do it so that we say, okay, what's something in between? And then we do the same experiment. We cut out the gastroc. Every day we feed them these nutrients, a very specific amount, either the optimal amount, the moderate amount, or the least amount. And then we get them out to 14 days. We take out the muscle and we look to see how much the muscle hypertrophied. Sure enough, the optimal group that we're just feeding 3 nutrients that are designed to block sirtuin-1, we get about a 67% hypertrophy. In the non-optimal, the least optimal, we're getting about a 20% hypertrophy. So we're getting 3-fold more hypertrophy just by taking those 3 natural products, combining them slightly differently to get it to the point where we're maximizing muscle hypertrophy. So that's super cool. And so we were all like, all right, this is great. And the way that this is going to be working is we're increasing muscle ribosome mass, and that's allowing us to synthesize more protein and make our muscle much bigger. Cool, right? And then you measure ribosome mass, and it doesn't look that way. Here's our untreated group that I didn't show you in the last one, but it has a smaller hypertrophy than even the least group. It's about 10% hypertrophy, whereas the least had about 20% hypertrophy. The optimal had 60% hypertrophy. And here, what we see is ITS1 is actually going down as we get more muscle hypertrophy. This is a different measure of ribosome mass, which is 5-EATs. It's the 5' transcriptional spacer. And so what that shows us is the exact same pattern, that we actually have lower ribosome mass, even though we have a significantly bigger muscle. And so it can't possibly be that when we look at ribosome mass, that the reason that we have more hypertrophy is that we have more ribosomes. In fact, if we look at total RNA is lowest in the optimal group. So this is really, really weird. What it's telling us is that the drugs, the natural products that we used in this case, they didn't block SIRT1 and cause an increase in ribosome biogenesis that caused a bigger muscle. But somehow they're increasing the amount of protein that they can make at a given amount of ribosomes. So what that means, the way that we interpret that, is that you can do two things. You can increase the total amount of the ribosomes, or you can increase the efficiency of the ribosomes. So what this is telling us is that these three natural products are making your ribosomes more efficient at making protein. So for the same amount of ribosomes, we're making more protein. Okay, and so that's a really big shift in kind of the way that we think about this possibility that we're increasing muscle mass only because of ribosome biogenesis. We don't necessarily need to make more ribosomes if we can make our ribosomes work more efficiently. And one of the things that we've learned since doing this is that all of the ribosomal proteins actually get acetylated themselves. And so what we think we're doing when we're blocking SIRT1 is we're blocking the deacetylation of the ribosome. And in the deacetylated ribosome apparently isn't as efficient as the acetylated one. So now by acetylating the ribosome more by blocking the deacetylase, what we're doing is we're making the ribosomes work more efficiently. And so that's an entirely different way of looking at this area.